Correct. So let's check it out in terms of the shape function. So let's see what we can do now. So what we did in the previous video, we sort of had an element, or we had a structure with sort of one quadratic function, another quadratic function. So I'm going to just zoom in one of them, and I'm going to put it down here. Okay, so let's just put it down, and let's get cracking on this. First off, as well, I'm not just going to represent this in the normal X space. I'm going to represent this in a special space that I'll call psi. This variable psi, such that psi is -1 here, and psi is equal to 1 here, and psi is 0 in the middle. Okay, if this is nice in the middle, or doesn't matter where this node is. Whether I put this node, I'll call psi equals to 0, but usually it will be. So let's just think about this for now. This version of what's going on. Okay. And what we spoke about is we want to have it such that it's got these properties. If I've got a variable q1 here, a variable q2, and a variable q3, these are the things I want to solve for, but I want to have these properties that if I evaluate the field, if I evaluate at psi -1, equals -1, I want to recover only the value of q1. If I evaluate at psi equals to q3, I want to only recover the value of q3, and if I evaluate psi equals to 1, I would only want to recover the value of q2. That is now what we've decided on. Okay, so this is important to understand. I'm also just going to give numbers to these nodes so that I can reference to them, so that we can think about what we want to do. Okay. So first off, what we want to do is essentially when we think about this, we have Q1 information at this node that needs to propagate spatially, but in such a way that it has no contribution here and no contribution there. Okay. So this is important to understand. That's the first thing. So let's think about just information of Q1 at node 1, which is this Q1. That information that's associated with node 1 is Q1. Let's think about how we can make that propagate spatially so that it has the properties that we spoke about. So first off, what we want to make sure is, for instance, what we want to do now is we want to set up some function as a function of psi. Okay. And this is it. We want to make sure that it's this, but we want to figure out what is the properties that this thing needs to have, so that it at least will have this kind of behavior that we spoke about. So first thing that n1 needs to happen is if I evaluate n1 at psi equals to -1, which is at this node where it's supposed to have information, I would like this to evaluate to some number that if I multiply this thing by q1, I get q1 out. So this is the question. I want to say my displacement, okay, contribution, I'll call this u1, because this is now sort of referring to the contribution to the displacement field due to variable q1, or due to node u1, or node 1, sorry. Okay, I would like it to be such that if I evaluate n1, okay, if I have this field n1 and I multiply it by q1, if I evaluate this u1 at psi equals to -1, I would just like to recover q1. Okay, that's it. So you know what the answer is. There's nothing magic here. The answer is I want to make sure n1 at psi equals to -1 evaluates to 1. Okay, so that's the first property. So psi this must be evaluated equal to 1. Then I know it will have this property, that this information of q1 is now spatially carried over this domain. But more importantly, if I evaluate ever the field here at this field for psi at -1, I will recover just the value of q1. Now this has got physical meaning. Beautiful. Okay. N2, N1, other properties. I don't want q1 to have a contribution here or contribution here. So I want to say if I evaluate n1 at psi equals to 0, I don't want anything to be added here. I just want this to be represented by the information of q3. So when we start thinking about a field that talks about how q3 propagates, I would like to make sure that this field is the contributions is only due to that variable q3. So I want to make sure that n1, if I evaluate it, which is propagate information q1 over the domain, evaluates to a 0 here. Okay, it's a root, and I want to make sure n1 evaluates to a 0 here, that it also q1 doesn't have to be added to anything here at this node. That this information is only given by q2. So q1 must have a 0 contribution at this node, so that we have that property. So then psi equals to 1, I would also be equal to 0. And this way, what will happen is, if I think about what this implies, is Q1, this function N1 that we're going to set up, will have such a property that Q1 will be, or this Q1 information will be Q1 at this node, it will have that meaning, and it will propagate spatially over this domain in some way, and it will make sure that there's no contribution of Q1 here, and it will vary spatially over this domain and make sure that there's no contribution of Q1 there. That's a beautiful property of the field, because now everything has got a nice interpretable meaning. Okay, so this we can now sort of use. If you go and you say, let's think about, so this I can wipe off, this was just for motivation. Can we set up our field? Can we set up our field N1? Yes, we can use sort of what we learned from high school. Yeah, you say we can construct equation from its roots as a product of the roots. So we can say N1 psi is a product of its roots. The one root is psi, and the other root is essentially psi minus 1, or I could write it as psi and 1 minus psi. Doesn't matter. Okay, let's choose one. Let's choose this bottom one. Let's choose this bottom one. I think that's the one the textbook uses. I'm not even sure if it's using that one or not, but let's just use 1 minus psi. And I can just show you again, it's a root. If I plug in psi 0, this expression is 0, and if I plug in psi equals to 1, this expression is 0. This whole thing is then 0. Okay, but still I haven't checked now whether this is satisfied. So this checks this, and it checks this when I write it down like this. And please bear in mind, I don't want you to memorize these shape functions just from a textbook, or just look at them always and say this is what they are. If I give you an element with 5 nodes, you need to be able to apply these principles, because following this logic of what we're doing, and be able to construct them. That is important. Okay, so please make sure you understand what's going on here. Not just those are not just functions that are falling out of heaven. They really have very simple and basic kind of principles behind them, and this is sort of one version of it that you could use to understand them. Okay, more importantly, N1, if I evaluate now at psi equals to minus 1, it needs to evaluate to a 1. But what does it do if I evaluate this at this stage at psi minus 1? So let's say N1 at psi equals to minus 1. At the moment, it evaluates to 1 minus 1, okay, multiplied by minus 1. So this is then 2, and this is minus, so this evaluates to a minus 2 at this stage. So if I want to make sure that this N1 has the property that it evaluates to 1, I need to just divide by whatever this was when I evaluated it at psi minus 1. And it evaluated to minus 2, so I just divide by what I have there, minus half. Now I know N1 has got the properties that I want. Okay. Now I know that if I evaluate this expression at minus 1, what do I get? 2 minus 2 divided by minus 2 is just 1. Beautiful. They've constructed N1. Okay, there's our first shape function, which is carrying information of Q1, the values of Q1 across the space, such that it's 0 contribution there, it's got a 0 contribution there. Stunning. Alright, so minus a half psi 1 minus psi. Okay. Yeah, so this is essentially what we have. Let's go. I'm going to stop this video. It's already 9 minutes. So I'm going to stop this and let's do N2. Stop this and let's do N3. Okay.